Hello everyone. In this lecture, we will discuss the simplest experimental design called the completely randomized design or CRD. These are the aims of this lecture. As the name suggested, in a completely randomized design, the treatments are completely randomized across the experimental units. A CRD is commonly used to compare treatments when the experimental units are reasonably uniform. This design applies two of the three principles of the experimental designs: randomizations and replications. A CRD is the simplest experimental design. The analysis is straightforward and it can easily handle unequal number of replications among treatments. This unequal number of replications could be pre-planned or unplanned due to missing values. A CRD also maximizes the degrees of freedom of the residuals. This design assumes that the experimental units are homogeneous. If the experimental units are not homogeneous, the difference in treatments could be hard to detect and would require a large number of replications. The analysis of data from a CRD experiment is straightforward. We use a one-way ANOVA. When there are only two treatments, we can also use a two-sample t-test. We can use the result of ANOVA to evaluating the power of an experiment. The power is the ability of an experiment to detect the real difference in the treatment means. There are two common measurements that can be used to assess the power of an experiment. One is the estimate of the residual variance or sigma square. The estimate of the residual variance is equal to the mean of square of residual. The other is the coefficient of the variation or CV. A CV is a ratio of the spread and the mean of an experiment. A CV is usually expressed as percentage. Because CVs has no unit of measurement, they can be used to compare the power of different experiments. In both cases, smaller value means higher power. However, these values have natural lower limits. This lower limit is set up by the natural variability among the experimental units. For example, a CV for a fertilizer experiment in rice is expected to be around 12%. Let's see an example. The response variable is the yield of potato. The explanatory variable is the type of fertilizers. We have 6 treatments and each treatment is assigned to the same number of plots. There are 36 plots. So we have 6 replications. This is the layout of the experiment. Each treatment are randomly assigned to 6 plots. First, we have to do some preliminary data analysis. We do this by plotting the data. If your experiment is laid out in a grid, you should always record the row and column information. This information will enable you to create a heat map. A heat map is a graphical representation of data where values are depicted by color. Heat maps make it easy to visualize complex data and understand it at a glance. This is a heat map for yield data from the potato experiment. A heat map is handy to detect a possible pattern in the data, especially the unexpected pattern. For example, this is a heat map for yield in a maize trial. This low yielding area were due to water ponding. For the potato experiment, there is no systematic or spatial pattern in this data. We can compare the heat map of yield with the field layout. Based on these two heat maps, we can see that treatment 1 tends to have lower yield than others, while treatment 5 and 6 tend to have the highest yield. We can create a box plot to check for outliers and possible mistakes. For example, this is a box plot for flowering time of Brassica carinata in multiple locations in 2018. From these box plots, we can see an obvious mistake in this data, as the flowering time was more than 400 days. It turned out that the year of harvest had been wrongly recorded as 2019 instead of 2018. After fixing this outlier, the data now look fine. The box plot for the potato experiment does not show any outliers, so we can now analyze the data. We can see from this plot, treatment 6 has the highest mean yield and treatment 1 has the lowest mean yield. Once we check the data, we can run the one-way ANOVA, the null hypothesis, the alternative hypothesis, remember, this does not mean it means at least one treatment is different. The skeleton ANOVA and the linear additive model Notice that the skeleton ANOVA match with the linear additive model. We can check for the assumption using residual plots. Normality, the points are close to the theoretical quantiles, so the data are relatively normal. Homogeneity. There is no pattern in the residual versus fitted value plots, and the ranges of residual are relatively the same across fitted value. So the homogeneity assumption is met. Independence. The residual versus order shows no obvious pattern. The residuals are relatively random. So the independent assumption is met. The ANOVA table. This match the skeleton ANOVA. For 5% significant level, the p-value is less than 0.05. So we have enough evidence to reject the null hypothesis. We can conclude that there is at least one significant difference among means at 5% significance level. However, we don't know which means are different. Now, can you do this?